So again, welcome to our last session of the day with two more very interesting talks. So I have the pleasure of introducing Fernando Santos, which is now an assistant professor at the University of Amsterdam, right? And he was a postdoc at Princeton University, and he completed his PhD in Lisbon at IST under the supervision of Francisco Santos, which is a name, by the way, I must admit, the first time. Sometimes I confused and I called him Francisco and not Fernando. So that's why probably why he went to Amsterdam, so not to be confused. And I will just say, incidentally, Francisco will also be, the old supervisor, Fernando, will also be an invited speaker at the conference. And the two topics are related, although they are not the same. So this will also be like Joanna's talk and Marcos. This will also be a topic that if you, something that interests you, you might follow later on. So he's going to talk to us about the dynamics of cooperation and fairness on networks. So I hope you all cooperate and be fair with Fernando. So the floor is yours. Thank you so much for accepting the invitation.
Thank you very much, Pedro, and for the invitation, for the introduction, and thanks everyone for being here. I'm really excited to be here today, not only because it's an in-person lecture. Nowadays, it's quite rare. But also because it's in Portugal. So I'm now in Amsterdam, so it's always really nice to come back and to present here. So in this tutorial, I will present on dynamics of cooperation and fairness on networks. And I must apologize in advance. I will sacrifice a lot of the mathematical details to focus more on the intuition for some of the classic results on this field. So hopefully we can use this tutorial as an entry point for people that would like to start to know more about this field, and also for people that have been working on these that they can use as a refresher of previous concepts. So this is the plan, not yet. First, in the first part, I would like to tell you about what is evolutionary game theory, and then we will focus on a cooperation dilemma. So we will see that in this dilemma, cooperation is socially desirable, however, it is quite hard to incentivize. And here we will focus on a game called the Prisoner's Dilemma. That is a fairly simple game, in the sense that it is a two-player game. It only has two strategies, and it is a symmetric game. We will then move to networks, and we will see how specific network topologies might facilitate the emergence of cooperation in this setting. Then in part two, we will move from cooperation to fairness. We will explore a multiplayer ultimatum game, and I will use this game in a way to provide the endpoints of a spectrum of games that can be more simple or more complex. I think there's some echo. If I turn this off, does it help?
Nico, maybe you can mute your computer because you have the microphone.
Oh.
I'm not sure it's that. Maybe I can ask the technical staff, but you have your Zoom with a microphone, so maybe your own computer is.
Oh.
Again, I cannot be sure of that. I'm just trying to.
Okay, I think it's funny. I thought this was also on, so I thought it was this.
But if you need anything, let us know.
Okay. Okay. Is it okay, the sound? Can everyone?
Yeah.
Okay. So we will focus on the second part on a fairness dilemma, and as I mentioned, this game will be on the other spectrum in terms of game complexity. So here we will have a multiplayer game, a game where strategies will be continuous, and the game will be asymmetric in the sense that players will play in different roles. And then also here we will be focusing on how network topology might provide an incentive for people to play more fair strategies. And then finally, and unfortunately I won't have much time to go to dive deep into these topics, but I would like to point some recent directions in the field of games on networks that I find particularly exciting. So we will be focusing on, I will just provide some pointers to games and higher order interactions, and also games on multi-layer networks. So this is the plan for the next hour. So let's start by what is evolutionary game theory? And maybe even before, let's start by what is game theory? And here we have game theory 101. And I did change the slide after Eugenius and Martha's talk to be consistent. So the goal of game theory is very generally to understand how will strategic individuals play games in a rational way. So let's see a very, very simple example. So let's say that we have two players, blue player and the red player, and they might choose between two different strategies, either C or D. So this is a payoff table, as typically is presented in the simplest games in game theory. So we have the strategies, either C or D, and then these numerical values will correspond to the payoffs, so the returns that each player will receive when they select a specific combination of strategies. So the rows will correspond to the strategy used by the blue player, and the column to the strategies used by the red player. For example, if the blue player plays C and the red player plays D, then the blue player will receive 0 and the red player will receive 3. Now, one typical analysis that is done in classical game theory is to look for the equilibrium, so the state where we expect players to get stuck in. So these are also called the Nash equilibrium. These are the combination of strategies that no player has any incentive to unilaterally deviate from. And for this game, we have two of these equilibria. We have the state CC. So if both players select strategy C, they both receive a payoff of 4. So there's no incentive to deviate from these. The one that deviates will, instead of earning 4, will receive 3. Also, DD is an equilibrium. If they both play D, then the one that moves goes from 2 to 0. Now, this is a typical analysis done in classical game theory. Okay? We assume that players know the payoffs, they know the game, and we are trying to figure out how will they act rationally. So what are the strategies that they are most likely to use, assuming that they know the game. A different approach would be to assume that players play on populations. They start with some random strategy, and they imitate the ones that are most successful in that population. Okay, so they don't need to know all the details about the game. They just need to observe their peers, and they might try to imitate the ones that are most successful. One example of question that we can ask here is, how do individuals in a population change their behavior over time, depending on what others are doing? Maybe a more specific question for this game, we could ask, for example, if there are 50% of players playing C and 50% of players playing D, do you expect the number of C individuals to increase, decrease, or remain the same? Maybe we can think about this question for a couple of seconds. Anyone has any ideas? So who says that if there's 50% of C's, 50% of D's, who votes for the increase of C's? Who votes for the decrease of C's? Anyone? Okay, there's some hands for the decrease. So the goal is that I won't give you the answer for now, but just think about the question. This is a classic question that people ask in evolutionary game theory. From a given state, do we expect the fraction of usage of a certain strategy to increase, to decrease, or to remain the same? And I will give the answer in a couple of slides. So evolutionary game theory, as the name indicates, combines concepts from evolutionary biology and game theory. From evolutionary biology, it borrows the idea that through natural selection, the genotypes of the most fit individuals will spread in the population. Now, the key point, however, is that the fitness from an individual point of view also depends on the traits, on the behaviors of others. So fitness cannot be measured in isolation. It depends on the frequency of other traits in the population. This is perfectly clear if you think about the relationship between a predator and a prey, or between here a hummingbird and a specific flower. So the best strategy for the predator, of course, depends on what are the strategies or the behaviors being employed by the prey. And now you can start to realize that this is quite similar to what we have seen in game theory, where the best strategy to a specific individual depends on the strategies that other individuals are using. So this combination of natural selection and game theory started to gain shape in the 70s. John Maynard Smith and George Price suggested this combination, suggested the idea of using game theory to understand evolution through natural selection, and since then the field has bloomed. Now, one fundamental concept in evolutionary game theory is that of the replicator dynamics. So the replicator dynamics will allow us to understand what will happen to the fraction of individuals using a certain strategy. How will that fraction, assuming that the population is large and individuals interact, everyone interacts with each other, what will happen to the fraction of different traits? This is the replicator equation. So let's unpack this. So this is the differential equation, which means that this is defining the increase of a certain strategy, in this case, the dynamics on the strategy C. So if this is negative, then it means that strategy C will increase, the representativeness in the population will increase. If this is negative, the fraction of C individuals will decrease. So let's unpack these. We have X, which is the fraction of individuals using strategy C in the population. We have FC of X, which is the fitness that an individual using C in that population is gaining. And here by fitness, I mean the average payoff in many, many encounters with random opponents. And we have F bar C, which is the average fitness in the whole population. So what this is telling us is that we are assuming that the fraction of C individuals in the population will increase if the fitness of C is higher than the average fitness in the population. So X here, this is always positive. This is a fraction between 0 and 1. So all that matters for this equation is the sign of this difference. Okay, the difference between the average fitness of a C individual and the average fitness in the population. Now this equation, the replicator equation, replicator dynamics, was proposed in the context of biology, again, to understand how traits evolve through natural selection. But nowadays, it is also quite common to be used in social sciences, in economics, to understand how in the population of humans, how behaviors evolve through social learning or through imitation. So this is applied both in evolutionary biology, but also in many other fields. And let's now see one example of the application of this replicator equation. So here we have a payoff matrix once again, and this is exactly the same game as the one that I presented in the first slides. So if we plot the replicator equation for this matrix here, we obtain something like this orange curve. So we have on the horizontal axis the fraction of C individuals in the population. It goes, of course, from 0 to 1. And we have the replicator on the vertical axis. So you can see here that there is a negative region. So there's a region where we expect the fraction of C to decrease, to move to the left. And there's a region where the replicator is positive, where we expect the fraction of C to increase, to move to the right. So this is what is called the coordination dynamics. So we expect the fraction of C individuals to naturally evolve to a state where everyone adopts C, provided that we get a minimum fraction of C individuals in the population. And notice that this also makes more clear the answer to the question that I posed in the beginning, right? So the question was, if we have 50% of individuals using C and 50% of individuals using D, what we expect for this fraction, and the answer is to decrease, right? So if you have 50% of C and 50% of D, then the population will most likely move to the left, so the fraction of individual C should decrease. So there were not many answers, but For those of you that internally thought that the right answer was decrease, you were right. Now let's see another example of a game. And this is the very famous prisoner's dilemma. This is the payoff matrix corresponding to the prisoner's dilemma. And please don't focus too much on the specific numerical values that I have here. What is important to retain about the prisoner's dilemma is that it has a single Nash equilibrium. So the Nash equilibrium of this game is DD. If both players choose D, and here by D I mean to defect, then they both earn 3. The one that deviates earns 0. So there's no incentive to deviate from this DD equilibrium. So this is also the state where we expect our players to end up in. Sadly, however, the social optimum, the combination of strategies that would maximize the payoff, the sum of payoffs in the population, is CC. Okay? It would happen when both individuals cooperate with each other. So if they both cooperate, they both receive 5. This is why we have a social dilemma here. So from the rational point of view, we expect individuals to defect, but it is desirable that they cooperate with each other. Again, this was an analysis based on classical game theory. We can again resort to the replicator dynamics and to evolutionary game theory. We can plot the replicator dynamics of this payoff matrix, and we will obtain this very set plot. So you can see here that the curve is negative, so we have 0 here. So our expectation is that over time, it doesn't matter the fraction of cooperators that we have in the population, our expectation is for the number of cooperators to decrease. And this is a game that became quite famous, not necessarily because of the metaphor of prisoners, but because this is a dilemma involved if we think about altruism, if we think about people having a cost to helping others. In this situation, however, let's say that we have one individual helping another. Let's assume that this individual pays a cost C to provide a benefit B to the individual that is being helped. And let's assume that B is higher than C. So the benefits of cooperation are higher than the costs of cooperation. If we now input these values into this payoff matrix, then we obtain, and provided that B is higher than C and C is positive, we obtain the exact same, or a matrix with the same properties as the matrix that I presented before. So again, it is socially desirable to cooperate from the rational point of view, and from the evolutionary point of view, we expect individuals to defect. And this is a fundamental question and problem in economics. If we want to design incentives and institutions that incentivize cooperation, it is also a fundamental question in evolutionary biology. If we want to understand why individuals around us, both in human populations and in other species, how come that these individuals evolved to help others? So if we have a well-mixed population, we expect the population to end up in full defection. And then the question is, can networks somehow help? Can networks provide justification for individuals to cooperate in reality? And this is what we are going to see in the next slides. Maybe you can stop. We can maybe take one question. If there is any question from, I'm not sure if this harms the logistics. I can also wait for the end if it's easier.
You can do as you please. So if anybody has a question. Microphone.
I was asking if I could see the previous equation.
Yeah, there's a typo here. This shouldn't be here. You're right.
Ah, okay.
Yeah.
Okay.
Oh, yeah, this is another version. You are completely right. Yeah, sorry. This is a typo. The PDF that I provide will be corrected, so this shouldn't be here. Thanks. Okay, I will wait until the end to get more questions. So what we are going to look into now is into populations, where individuals are still going to play a prisoner's dilemma, but instead of assuming that everyone can interact with everyone else with the same probability, we will assume that individuals are organized in a network, in a graph. And this network will impact the evolutionary dynamics in at least 2 ways. So we will assume that individuals in a particular node will only receive the payoff depending on the strategies that neighbors are using. And second, we will assume that evolution will only take place by having strategies replacing adjacent sites. Okay, so a strategy in one node can only replicate to neighboring sites. And once again, the question is, can this setup somehow help cooperation to evolve? Now, one of the first works in this field was done in 1992 by Martin Novak and Robert May. And what these authors considered was that players are organized in a two-dimensional lattice, something like this, where they can interact with the 8 closest neighbors. So they consider a Moore neighborhood. Individuals can be cooperators or defectors. They will accumulate payoff based on the strategies used by all of their neighbors according to this matrix. So this matrix is slightly different than the one that I presented before, but this preserves all the properties of the prisoner's dilemma. What's important to retain here is that there's a parameter B here that in this case will work as a temptation parameter. So this controls how much a defector will earn when playing with a cooperator. So if B is higher, it's more tempting for individuals to defect against cooperators, so it's harder in principle to incentivize cooperation. And the authors here considered a synchronous update. So they consider that everyone plays with everyone around them, again, considering a Moore neighborhood. And after everyone accumulates payoff, every individual will change their strategy to the strategy of the neighbor having the highest payoff. Okay, so I look around, I identify the neighbor that is earning more payoff, and I will update my strategy to that of that neighbor. Here we see one example of payoff calculation. So we can see here, for example, that we have this cooperator earning 5. And by the way, here, this combination was cherry-picked. So here we have a cluster of cooperators. This is important for the result that I'm going to show next. So this cooperator here is earning 5 because it is surrounded by 5 other cooperators. Okay? So remember that one cooperator receives 1 for each adjacent cooperator. And this defector here is receiving 3B. Okay, so the defector is earning B for each cooperator around, so there's 3 cooperators in the neighborhood, so this explains the payoff 3B. What's interesting here is that if we now think about how these strategies will replace each other, you can notice that this cooperator, this defector here, will adopt the strategy of this cooperator, provided that B is lower than 5/3. And this corresponds to a B close to 1.66, which is interesting, right? So it means that before we have seen that if the population is well mixed, there's no way that a cooperator can fixate. But now, because there are these clusters of cooperators, it might be possible that if a cooperator is surrounded by other cooperators, then this cooperator might have higher payoff than the adjacent defectors. So cooperators can invade defectors when starting from these small clusters. So this spatial arrangement can provide an incentive for cooperation if cooperators are clustered together. This is a figure from that paper for a 200 by 200 square lattice, and for a value of B between 1.75 and 1.8. You can see the clusters of neighbors in blue surrounded by lines of defectors. This is a time series, also in the same paper. Even if B is higher, we can see here that the frequency of cooperation in the population remains stable around 0.3, which is, it's not the majority of strategies in the population, but still it's higher than what we would expect from a well-mixed population. Now this was a first attempt to model this dynamic of cooperation and defection in a lattice. Of course, this is a highly idealized scenario. Every individual has the same number of neighbors. Soon after, there was another work by Kim and co-authors, considering that a single node in this lattice to be an influencer. So in general, everyone has the same number of neighbors, everyone is in a square lattice, but there is one node that is being observed by a lot of other nodes in the population. And this leads to, again, they observed very high levels of cooperation, but what's interesting is that they found that these led to certain drops in cooperation followed by a slow recovery, okay, something like this. So this is the average of many simulations. And the reason is that from time to time, this defector might turn, this influencer might turn into a defector, and because this defector is observed by many nodes in the population, as soon as the influencer shifts to defection, many others will follow, so cooperation will drop drastically, and then it will recover again. And I'm pointing this work out also because this was a first attempt to somehow try these dynamics in more realistic networks. And these efforts continued. So in 2005, Pedro mentioned Francisco Santos, that will be here tomorrow or Thursday. In 2005, there was this work showing how these dynamics of cooperation and defection plays out in scale-free networks. So the authors considered heterogeneous networks. The idea is similar as the previous work. So nodes will accumulate payoff, and they will imitate nodes around them based on the difference between the payoff that they are obtaining and the payoff, the accumulated payoff of their neighbors. And the game to be played is also similar. What they found, and well, as the name indicates, scale-free provide an unifying framework for the emergence of cooperation. So the conclusion here is that indeed, scale-free networks are quite efficient in enabling cooperation. And the reason is that, which is quite interesting, this is due to some so-called age correlations in the network. So if networks grow through preferential attachment, then what happens is that nodes that are older will have more connections, and at the same time, they will tend to be connected with each other. So basically, we will tend to have this pattern here where you have two hubs connected with each other. And this is beneficial for cooperation, and this is a very quick intuition for that. This is beneficial for cooperation because the hubs that will get surrounded by cooperators will, of course, have a higher payoff than the hubs that are surrounded by defectors. So hubs that are themselves cooperators and surrounded by cooperators have a higher chance of being imitated. And through this pattern of imitation from hub to hub, it's likely that cooperation fixates in these populations. So here we can see for different values of B, and we have the frequency of cooperators in the vertical axis. We have in red scale-free networks, in black regular networks for two different network sizes. You can see that if we increase B, the temptation of defection, then for regular networks, cooperation suddenly drops for a low value of B, whereas for scale-free networks, cooperation is able to be maintained in high levels. And also notice, I mean, maybe you are asking, okay, so these are fairly small networks with 128 nodes, so these are not even scale-free networks. But the reason is that even in small networks, it's possible to have these age correlations. So the nodes that have more neighbors tend to be connected with each other. So even in these small network cases, we can observe these resilience to the invasion of defectors. About the same time, soon after, there was another very influential work where Isashi Atsuki and co-authors proposed a very simple rule to determine which networks enable the fixation of cooperators in the population. And I'm also pointing out this work, of course, because of the simple rule that is quite elegant, but also because this work clarifies how different strategy update mechanisms might lead to different, completely different fates for cooperation. So the authors consider one update called birth debt. So with this update process, first it is selected one individual to reproduce proportional to its fitness, and second, one neighbor of this individual is randomly selected to, well, quote unquote, die and be replaced by the first one that was selected. And they also consider the death-birth process, where first a random individual is selected to die without any concerns about fitness. And second, a neighbor of this one is selected based on fitness to replace the one that died. And these seem quite similar rules, but we will see that the result is very different. Let me give you an intuition for these. Let's say that we have this very simple network. Here we are assuming that cooperators pay a cost C to provide a benefit B to neighbors. So for example, here we have a cooperator that is cooperating with both neighbors, so minus 2C, but is only receiving cooperation from the left neighbor. So that's why we only have here B. If we follow the birth-death process, first we select a random individual proportional to fitness. And note that here we are interested in understanding how the number of cooperators will vary. So we should focus here on what will happen in this boundary between the cluster of cooperators and the cluster of defectors. So first we select an individual proportional to fitness, and most likely between these two, this one will be selected much more often, right? So the payoff is always higher. B is higher than B minus 2C. We assume that C is positive. And then we select a random neighbor to die, okay, randomly. So if we select the one on the right, nothing happens. The number of cooperators remains the same. If we select the one on the left, defection will increase. So the conclusion is that for a birth-death process, the boundary between a cluster of cooperators and defectors will tend to move in order of favoring defection. On the other hand, if we have a death-birth process where first we select a random individual to die, then things will be much different. So there's just a small deviation, but what will happen is that first we select a random individual, and this individual in the boundary can either be the defector or the cooperator with the same probability. Doesn't depend on fitness. So let's say that we select the defector, and then we select a random neighbor proportional to fitness. And now the story is completely different, right? Because now the decision is between selecting one neighbor earning 0 and another neighbor earning B minus 2C. So we will select the one with a fitness of B minus 2C, provided that this is higher than 0. And so there's a chance that a cooperator will replace a defector, so we can have the fixation of defectors. And this will happen if B over C is higher than 2. Here also the degree of this network, the average degree and the degree of all neighbors is 2. And what the authors find is that for a death-birth process, actually this rule is quite prevalent. So if B over C, the benefits over the costs of cooperation are higher than the average degree of the network, then cooperation stands a chance, and it's likely that cooperators replace defectors. Now, to conclude this first part on cooperation, let's recover what we had, replicator dynamics. So remember that in a well-mixed population, this was a very sad scenario where we would expect defectors to prevail. In 2012, Flavio Pinheiro and co-authors, and Flavio should also be here tomorrow or Thursday, they proposed a way of numerically compute the analogous of this replicator, but for a finite and structured population, okay, the so-called average gradient of selection. And this allows us to understand, at a global point of view, how will the dynamics change? And what we can observe is that if we consider an homogeneous network, so a network where every node has the same number of neighbors, then this replicator, this dynamic profile, will transform into one where we have a stable coexistence of cooperators. And this reminds the first result that I showed, where in the lattice, we had a stable cluster of cooperators. And they also found that for scale-free networks, we have this coordination. So if we have a critical number of cooperators, then it's likely that a lot of these cooperators or some of these cooperators are hubs, highly connected nodes. And so from here, the population will naturally organize to a state where everyone ends up being a cooperator. Okay? So the take-home message is that by considering networks, we completely change the dynamic profile of these cooperation dilemma, and indeed, networks can stabilize cooperation. So the key ideas so far, so we've seen evolutionary game theory and how evolutionary game theory is concerned with studying how strategies evolve through frequency-dependent selection. We focused on a prisoner's dilemma, where cooperation is socially desirable, yet hard to explain and incentivize. And we have seen that networks provide ideas or mechanisms for cooperation to be stabilized. This happens because clusters of cooperators are robust against the invasion of defectors. Heterogeneous networks that have these H correlations enhance cooperation. Depending on network degree and specific mechanisms that we consider for strategies to evolve, cooperators can invade. And finally, and in a way, to summarize the previous result, what happens is that networks can change the dynamic profile of this game. And before the second part, if there's any question about the first one. Thank you.
I wondered what happens if instead of the games being played totally synchronously, if they were played asynchronously, so in some random order of the edges, would a similar thing happen, or would it be quite different?
The results will be, so the updates are synchronous to the lattice. I'm pretty sure that for the other results, the updates are asynchronous. So what I do is, at least for the imitation, the game on the skill-free networks, first one node is selected, then a neighbor is selected, and one will imitate the other with a certain probability, and then this happens for another pair of nodes, and so on and so on. So updates in that case are not synchronous, and yeah, the results are synchronous. But that's a good question. I should have clarified that.
Thanks.
If the strategy, instead of being to copy the neighbor with the most profit, if it is that to adapt my state to the one in which I would obtain the most profit, given that everybody else stays the same, would the results be similar?
There are some changes. You are completely right. For this game, I'm not sure, but definitely things will change. So that happens, that's called the best response dynamics. So I formulate a certain model of my neighborhood, and then for that specific model that I have about the behavior of my neighborhood, I'd select the strategy that maximizes my payoff. So that will, I'm not entirely sure what will happen for these specific games, but in general, yeah, things might change. That's a great question.
And the second question, if you allow me, is what if we take into account that our neighbors can also think the same, and so we adapt to them, and if we do this an infinite number of times, is it possible to reach like a stable state?
Mm-hmm. Yeah, I'm not sure. That's quite complex. So let's go back to the first setting that I showed, the game theoretical analysis, where we were looking for the Nash equilibria. At that point, we were assuming that agents are really rational, so they do that type of reasoning. They have full information about the game. When we move to the evolutionary setting, the goal was to assume agents that are less rational in a way. So our trend was to move to a setting where they just observe what others are doing and they update accordingly. Then, and also remember that this framework appeared in the context of evolutionary biology, where we are talking about traits that replicate, that don't necessarily think. But then in social systems, but if we have these like theory of mind type of dynamics, where you reason about what the other is reasoning and so on, that places in a setting where agents are assumed to be extremely rational, which is a different setting than the one that I'm exploring here, where agents just resort to imitation. So I'm not sure what will happen for this specific game. My guess is that we will have more defection. So the best response for this prisoner's dilemma, the best response is to defect. So I'm assuming that less imitation, more rationality will probably increase defection. Does that make sense?
Yeah, thank you.
Yeah, thanks for the question. Yeah.
In evolutionary algorithms in general, a key aspect there is the crossover or the recombination. So perhaps in continuous strategies, is there also such a thing in these methods?
Yeah, that's an excellent question. So the difference here, in general, evolutionary algorithms are used to optimize. Here we are not dealing with an optimization process, so that's the first point. Here we are just like looking to how individuals evolve over time without necessarily optimizing. In fact, for the case of the prisoner's dilemma, evolution is not optimizing. On the contrary, it's leading to more defection. In this case, strategies are very simple. So in the strategy that I showed now and the ones that I'm showing next, there's no crossover. But that happens, for example, when there are more complex strategies, when you represent strategies with a vector, for example. So there are some models that consider that replication happens by some crossover, recombination, and mutation. Yeah. So that doesn't happen here, but there are works where evolution happens through that process. You're right.
Okay, thanks.
Thank you. Okay, so maybe we'll continue for now, and then there will be time for some more questions later on. So now let's jump to the realm of fairness. So now we will explore a game that will be multiplayer, strategies will be continuous, and the game will be asymmetric. Again, players will play in two different roles. And again, we will be concerned with understanding how network topologies will impact fairness. So now we will have this game. This is the Ultimatum Game. I'm not sure if you are familiar with this game. Is this familiar to someone? Okay, great. It's always better for the first time. So this is the Ultimatum Game. Here we have one proposer and one responder, and the game goes like this. The proposer has some resource. Let's assume that the proposer has money, for example, $10, 10 euros. And the proposer is offering a division of this resource to a responder. And then the responder can accept or reject. So if the responder accepts, then the resource is divided as it was proposed. If the responder rejects, none of the players will earn anything. So we can say that the strategy of the proposer is a value P, which is the fraction of the resource that is being offered to the responder. And the strategy of the responder is a value Q, which is the minimum fraction that the responder is willing to accept. Okay. So if P is higher or equal than Q, then the proposal is accepted and the resource is divided as it was proposed. So if P is higher than Q, then the proposer will keep 1 minus P. Okay. So the proposer will keep what he or she did not offered, and the responder will get P. If P is lower than Q, then the proposal is rejected and they will both earn 0. Okay. So the resource is removed from the proposer. Now, if again we go back to tools of classical game theory, we can assume that these agents are rational, and let's think about what are the expected strategies to be played. So let's first think about the strategy of the responder. So notice that for the responder, it is always better to accept. Right? So if the responder accepts, the responder will earn something. If the responder rejects, the responder will always earn 0. So we anticipate a very low value of Q. Close to 0, a value of Q that accepts everything. And the proposer, knowing about this, should offer the minimum possible, right? So the proposer should try to get to himself or herself the maximum possible, so P should also be very low. Notice that this is unfair, so this means that the proposer will get to receive almost all the resource. So here we are assuming that fairness corresponds to an equal division of the resource. Now, in reality, however, there's many works pointing out that people do not play like these in reality. Okay? When people play this Ultimatum Game, when people play in the role of proposer, they tend to make fair offers. When people play in the role of responder, they tend to reject low offers. In the paper, the original paper that introduced this game, the most common offer was 50% of the resource. and the low offers were rejected. And after these, there were many other works, experimental works, pointing out that people care about fairness in this game. People reject low offers, and people tend to offer higher offers than what classical game theory predicts. And once again, this is the prediction from game theory. This is also the prediction, I didn't show this, but if we assume a well-mixed population where agents imitate each other and so on, the prediction is also that we will end up in a state where everyone is unfair, everyone accepts everything, everyone offers very little. So the question is, again, can networks help to understand why people play this game in a fair way? One of the first works to study this question was by Karen Page and co-authors in Royal Society B in 2000, where the authors considered, again, lattices, either one-dimensional, as I'm showing here, or two-dimensional. As I mentioned here, the strategies are continuous, but let's for now simplify things a bit and assume that there's two strategies. One, the fair strategy, where an individual, when playing in the role of proposer, will offer P2 and only accepts P2. So any offer below this value of P2 is rejected. And there's also the unfair strategy, where individuals offer low, something below P2, and accept everything. So let's see what happens if, again, we have this cluster of fair individuals. So the accumulated payoff of this node here will be 1 plus P2. Let's try to unpack these to see why this is the case. So when this node plays with a left neighbor, the node will offer in the role of proposer P1. Okay, so the proposal is accepted. So this node will get 1 minus P1. And when this node offers in the role of proposer, this node will get the P1 back. So it will get 1 when interacting with the left neighbor. When interacting with the right neighbor, this node will get P2. So the fair node offers P2, the proposal is accepted, and when this unfair node offers P1, the proposal is rejected, and no one earns anything. Okay? 1 plus P2 is the accumulated payoff here. And then the same reasoning applies to the second node, to this fair node. Here, the payoff will be 2 minus P2. You can check these later. The point here is that now, if we again think in terms of imitation, about strategies with a higher payoff replacing the ones with lower payoff, we can conclude that it's likely that a fair node will replace the unfair node if P2 is lower than 1 over 2. Okay? And recall that our expectation was for values of P to be reduced over time. But now we are saying that in this spatial context, if fair individuals get clusters together, then P2, the fair strategy, can grow up to almost 1 over 2, close to the fair division, and still fair individuals can survive. So again, spatial structure and clustering of these individuals, of these fair individuals, might provide a mechanism for fairness to prevail. Now, so far, I'm only discussing pairwise games. I promised that I was going to show some multiplayer games. So we can also think about these dynamics of fairness and proposals being made to people in the context of groups. So if we think about economic or climate summits, group hunting, policy making in coalitions, in all these settings, we have proposals being made to groups. Okay? And there will be groups. So groups will be the entity in a way that must accept or reject these offers. And we can transform the previous game in this multiplayer context if now we assume that we have a proposer doing some proposal to a group of responders. So again, the strategy of the proposer will be P. But now we assume that individually, each responder will have a threshold of acceptance Q. And the ultimate decision from the group will depend on a mapping between these individual thresholds and a group decision. Now, the group decision can be arbitrarily complex. We can think about many ways of mapping these individual Qs to a group decision. We can think that the lowest Q is the one that prevails, the maximum Q is the one that prevails, the average Q is the one that prevails, and so on. So to simplify things, we will assume that the proposal is accepted by the group if at least m responders accept it. Okay. So here, for example, we have m equal to 2. So the proposal is accepted if we have at least 2 values of q lower than p. And this allows us to play with this m and test different voting rules. We can go from majority rules to unanimity rules, consensus rules, and so on. So in this context, if we keep m equal to 2, and if, however, we only have one responder accepting, then the proposal is rejected, and none of these players will earn anything. Okay? So this is the basic mechanism of this game. And again, why am I telling you about this game? So you can realize that this game is more complex than the prisoner's dilemma in many ways. Of course, now instead of having a dilemma of cooperation, we have a dilemma of fairness that is not necessarily more complex, but it's different at least. We have continuous strategies instead of just 2 strategies. We have a multiplayer game instead of a pairwise game. And the game is asymmetric. So now players are playing in these 2 different roles. In the prisoner's dilemma, everyone is playing in the same role. The only thing that distinguishes the players are their strategies. It's not that easy to come to derive analytical results in this context. We can do numerics, we can simulate. I can just give you an intuition for how we can simulate dynamics in this context. So each node will be characterized by a value of p and q. Again, these are values, continuous values that range between 0 and 1. Now we don't have binary colors, we have some shades. Initially, we can assign values of p and q sampled randomly from this interval to each node. And then for each individual a, selected in random order, we can select a random neighbor b. We can compute the fitness of a and b based on all possible interaction groups. And here by interaction group, I mean groups where individuals will play all together. And I will come back to these later in the context of higher order interactions. But here the idea is that one interaction group is defined by one node and its neighborhood. Okay. So one example of interaction group is the group centered in A. So A together with its neighbors will form one group. Another example is the group centered in B. So B we'll call A and they will form a group. Okay. So you can think about these groups as birthday parties, where one node will call all his friends for a birthday party and everyone will play this multiplayer ultimatum game. So we will compute fitness, and fitness here will be the accumulated payoff in all possible interaction groups. And then we will assume that A imitates B, meaning A will adopt the value of P and Q of B with a probability that is proportional to the difference between their fitnesses. And then there's some noise that is added to the value being imitated. And this puts us closer to this evolutionary setting where we have some mutation or some noise added to the values that are imitated. So this is the general mechanics of how we simulate these, and then we will be interested in understanding how the average values of P and Q will evolve over time. Now let's think a bit more about how these groups are formed. And what I'm going to argue now is that the way that these groups overlap with each other is important for fairness in this game. Okay. So here I'm representing 2 different very small networks where we can see that the overlap between the interaction groups is different. So on the left, we have groups not overlapping that much. On the right, we have groups overlapping to a greater extent. And this means that different levels of overlap will translate in different levels of influence between individuals. So on the left, we have a setting where we can say that we called it structural power. Maybe it's not the best name, but definitely on the left, there's less influence between the nodes. And the reason is that nodes will face different opponents in different interaction groups. Compared with the right, where we have a setting of high structural power, meaning that individuals will always face the same individuals in different groups. So if I'm facing some friend in all interaction groups where that friend will play, I have a stronger influence over that node. So we can define this idea of structural power as the structural power between of A over B as the number of groups where A and B meet over the total number of groups where B plays. So if A takes part in all groups where B plays, then A has a lot of influence over B. If A never meets B, then A has no influence at all over B. Right? And what we can observe is that actually the structural power, this level of overlap, matters regarding the strategies that evolve in the population. In particular, if networks have a higher level of structural power, then we will have fairer strategies emerging. So here we have on the left the average value of proposal, on the right the average threshold value, Q, and each of these bars corresponds to a simulation played on a network with a different level of structural power. And we generate different networks through simulated annealing. So we start with a random network, we rewire some links. If this rewiring step improves the structural power of the network, we accept that step, otherwise we don't. Now, one intuition for these overlap, and this is just an intuition, I mean, it's not that easy to show that this in fact occurs, but one intuition is that if there's a lot of overlap, if there is a lot of influence between nodes in these networks, then it's easier to punish unfair individuals. So let's say that I am unfair. In my neighborhood, I have someone that has a high Q, so it starts to punish unfairness. If this individual doesn't have a lot of influence or structural power over me, I don't care. I face this individual in a single group, but then I will have many other groups where I will not face this stubborn guy. On the other hand, if we have networks with high levels of structural power, high levels of overlap, then I will systematically face this fair individual. So my only hope is that I increase my level of P so that I can have some offers accepted. So in a way, high levels of structural power provide the means for punishing unfairness to be effective. Okay, and now let's move to exploring the opportunities that this game being asymmetric provides us. And in particular, what I would like to explore here is how can we use network properties to assign the role of proposer or responder. So remember that this game is asymmetric in the sense that we have role 1 proposer, role 2 responder. If we are playing in well-mixed populations or in regular graphs where every node is essentially the same, then what is often done is it is assumed that individuals play in one of these two roles with the same probability, or they play both roles at the same time. However, if we have heterogeneous networks, we can start to think about how, depending on specific network positions, how can we bias the assignment of these roles. So we can think, for example, about having the means to be the proposer. So the proposer is someone that is the first mover, that has some resource, something to propose. Perhaps it is the case that being in this position is correlated with network position. So those that have higher degree also have the resources to be proposers. So what we can do is, and this is just one example, so let's say that we have here a group formed by A, 1, 2, 3, 4. These nodes here have a different degree. So we can have a function that assigns the role of proposer based on degree, for example. So here we have a parameter on the horizontal axis that controls how much the role of proposer depends on degree. On the vertical axis, we have the probability to select node A, 1 or 2 as the proposer. And by tuning this parameter, we can go from a setting where low degree nodes are the proposers to a setting where high degree nodes are the proposers. And what we can observe is that if highly connected nodes are the responders, then it's easier to have fair proposals. We can also see that if by default, if by construction, by design, the proposers are the highly connected nodes. So again, if these are the nodes that have the resources to be proposers, then we can play with them, we can play with voting rules to reintroduce some fairness. Again, an intuition for these, and this is a very, again, rough intuition. So we can think about the same principle of two stars being connected and on a scale-free network. Again, the same applies as what we saw in the case of cooperation dilemmas. If we have here some hub surrounded by individuals that are offering, that have a high P, then it's likely that this hub will be imitated with a higher probability. But now the key point is that for this to happen, we need to guarantee that the leaves are proposers. Okay? This only happens if these are the ones that are being fair and offering a lot to the center responder. So this provides an intuition for why having the leaves as proposers might improve the levels of fairness that we observe. This happens for the multiplayer ultimatum game, but actually there are some previous works pointing out that the same principle occurs in the pairwise ultimatum game and also in a very similar game called Dictator Game. Okay, again, let's stop for a bit. Let's revise this second part. So what we have seen here was that this ultimatum game suggests a fairness dilemma. And in this dilemma, fair strategies are used in practice. There's a lot of experiments pointing out that people are fair. However, this is hard to justify in well-mixed populations. We focused on a multiplayer version of the ultimatum game. This game is more complex than the present dilemma in the sense that it is a multiplayer game, it is asymmetric and considers continuous strategies. So this was a way of presenting you a range of methods that goes from simulating a very simple game to some other works that consider more complex games. And we have seen that also here, networks are a mechanism for fairness to emerge. Clusters of fair individuals can be stable. Group overlap, defined by network topology, impacts levels of fairness and can provide also a mechanism for fairness to evolve. And asymmetric games suggest new ways of assigning roles in heterogeneous networks. And now I would just like to really run over these relatively recent directions that I find quite exciting in this field of evolutionary games on networks. The first one is games and higher order interactions. So if you remember correctly, here we found that the way that groups are formed actually plays a role in the evolution of fair strategies, but the way that we were forming groups here was quite specific. We were assuming that a group is formed by selecting a focal node and considering its neighborhood. Now, of course, this is not the most flexible possible way of doing this. We can ask, for example, does it make sense that every node in a network can be a focal node, inviting these friends? So a more general way would be to consider hypergraphs, for example. So hypergraphs are an extension where instead of having a link connecting to nodes, you have hyperlinks that might connect a set of nodes, not necessarily a set of size 2. So here we have one hyperlink with connecting 3 nodes. And these might provide more flexible ways of forming nodes, of forming interaction groups, in the sense that one hyperlinked might define an interaction group. And there are some recent works addressing these. For example, these work by Julie Bourdieu et al. 2020 Entropy, and also very recent work from last year where Unai Alvarez Rodriguez and co-authors considered public goods games, which are in a way multiplayer versions of the prisoner's dilemma played in hypergraphs. Another direction is to consider multi-layer networks where you have different games being played in different layers. So until now, we assume that every individual, every node in a network is playing the same game. In reality, we might belong to different networks. We have our network of coworkers, our family network, our friends network, and so on. So perhaps we play different games on these different networks. And then the question is, how will the payoffs of these different interaction networks combine to determine how I will update my strategies? So here on the left, we have actually a plot from a paper of Marta Santos that I'm not sure if it was here in the morning, and Sergei Dorogatsev and Joseph Fernando Mensch, where they consider a setting where there's two layers. There's a snowdrift game played in one layer and a prisoner's dilemma played in another layer. Then the question is, what happens to cooperation when individuals in one layer might imitate a strategy being adopted in another layer by their neighbors? And on the right, a setting where you have two prisoners' dilemma being played in two layers, however, with different game parameters. So some pointers for these works. So there's this 2012 paper by Jesus Gomez Gardeñas studying what happens when there's many layers where there's a prisoner dilemma being played in these different layers. And they show that if we increase the number of layers, we provide some robustness for cooperation. Again, this work by Marta Santos, Sergei Dorogosev, and Jose Fernando on biased imitation in interdependent networks, where you have a prisoner's dilemma, a snowdrift game, and how if individuals by mistake imitate the strategy being used by neighbors in the other layer, how that might actually lead to relatively high levels of cooperation in settings where a prisoner's dilemma alone would not promote cooperation. And a very recent work by Kisu and co-authors of this year, where they developed some analytical methods to study the analysis of cooperation dynamics on top of multi-layer networks. So if you are interested, you can follow these works. Again, this was just a very fast overview of these directions that I find quite exciting. So to conclude, we've seen here today, and hopefully now we can have some questions, but also some coffee break until the next workshop, tutorial. So we started with evolutionary game theory. This provides a set of tools to study frequency-dependent selection of traits and strategies. We saw a cooperation dilemma, a prisoner's dilemma, where cooperation is socially desirable yet hard to incentivize. And then we have seen that specific network topologies can sustain cooperation. Then we moved to the realm of fairness. We considered the fairness dilemma that is slightly more complex than the prisoner's dilemma. And once again, networks might provide some ideas about how to enhance fairness in these settings. And some directions that unfortunately I didn't have time to explore here, but that are quite exciting. And this was a 1 hour tutorial. If you are interested in this topic, you can find here some resources that go in detail about some of the works that I mentioned. The PDF will be available, I believe. Also, there's some talks related with this subject this week. So tomorrow, Tomás Vieira will present on cooperation, reputation, and lies on networks at 11 a.m. And Wednesday, as Pedro mentioned, Francisco Santos will present on climate dilemmas on top of complex networks. And thanks everyone for listening.
So we have time for questions now, although I should say, unfortunately, no coffee break between this and the next talk. So it will only make the next presenter's job harder. So you will be the coffee break. Okay. So please, if you have any questions that you would like to ask. So is this network cooperating or defecting to a... Is it well mixed?
Yeah,
I think it's a multi-layer network with some mathematicians, computer scientists, physicists, and...
Mm-hmm. It's a temporal network, so questions will come later, maybe during the week.
And analyzed with the next talkers, right?
Yeah, and well, just if you have any question after, send me an email. I'll also be around over the week, so we can chat.
Thank you so much for talking. I would like to ask for you. It's not so clear for me. When I'm talking about the high power structure of the networks, this can't be a measure of the robustness of neural network.
Sorry, I didn't.
We can use the high power structure how a measure of the robustness of the network. I am curious about that.
Yeah, that's a great question. I'm not sure. Yeah, we didn't use to test robustness, but yeah, that's an interesting question. So the network, by improving the structural power measured, the network becomes more modular. So maybe against targeted attacks that break bridges between modules, the network can become disfragmented. So in a way, my guess is that improving these measure on network can make it less resilient to these targeted attacks. But that's an excellent question. I don't fully know the answer.
Okay, I really appreciate it.
Thanks very much. Very interesting presentation. I was curious about the idea of fairness because, like, seemingly from the Ultimatum game, it just emerges without any indication from the rules of the game, right? It's people just think it should be fair, and there's no indication in terms of their outcomes that the fairness should be there or not. I'd like to know if there's studies on fairness from a different perspective other than the experimental one. Like if there's some sort of theory on how people think something is fair or not in terms of a game and incentive. Or...
Yeah, that's a great question. So I think one underlying assumption is that the proposer and the responder are somehow equivalent, so they should deserve the same level of resource. That's why the equalitarian division is considered to be fair. So there is this resource that comes from nowhere to the proposer, and the proposer is just distinguished from the responder in the sense that the proposer needs to propose the offer. There are some works doing experiments where the proposer needs to somehow earn that resource. And in that case, I think proposals tend to be more unfair in the sense that people believe that the proposer should keep a higher value, a higher share. So that's maybe one potential work that would be interested in a way changing the nature of the proposer and making it making that role in a way deserving a higher resource. But in general, yeah, the works assume that they should deserve the same level of resource. So fairness is the equalitarian division. But yeah, that's a great philosophical question. Thanks.
Okay, so I propose to, okay, sure.
Okay, I will try to be concise, but my view of this is that at the end, maybe we will add multi-layers and then hypergraphs and policymakers and a lot of things in this game theory. How do you tackle everything at the same time, like building different games happening at the same time in different layers with different topologies and fairness, and how do you approach such complexity?
Yeah, no, that's a good question. So I didn't mean I didn't want by any means to convey the idea that it is always desirable to make the models more complex. So I really love all the simple models that I presented in the first part. I think that there are some particular issues that maybe can be better modeled by considering different approaches. So I don't mean to combine higher order interactions with multi-layer to make everything at once. Of course, that will be intractable, and there's a lot of beauty about studying these simple models. But for particular goals, like for instance, to model the interaction groups, I guess that simple links might be too restrictive. So there's some merits in considering these higher order interactions. But then it will be really hard to have higher order interactions and multi-layer networks and more than 2 layers at the same time. I agree. So I don't know the answer how to study these, especially analytically. So my goal and the reason that I find these appealing is that it might allow to model specific details of our social relationship that a simple graph is not able to. And like the multi-layer network, for example, it's useful if we play different games, and we do play different games with different people. So it's interesting to think about how the interference of the payoffs in the different layers might interfere with each other, how the correlations between the two networks in terms of degree, for example, might change the properties of the game. So these alone would be super interesting, even not considering higher order interactions here. So yeah, I would be very careful adding complexity to these models. I completely agree. So I don't think this answers the question,
no.
but
I mean, I know that it gets really, really complex.
Yeah.
So plenty of research opportunities still, right? Okay, so let's thank the speaker again. Thank you, Fernando. And I would ask, if you don't mind, so Ben and Naomi, if you could come forward.